Maximum coverage is a fundamental problem in combinatorial optimization. The setting is familiar. We have m points, here labeled 1 through m, and n sets over these points. Additionally, we have an integer cardinality constraint, k. The goal is to select k sets ae1, ae2, and so forth up to aek, maximizing the total number of points covered, that is, maximizing the size of the union of these sets. Let us compare and contrast max coverage with the set cover problem discussed previously. In set cover, the goal was to cover all of the points using the minimum number of sets. In maximum coverage, the goal is to cover as many points as possible with a limited number of sets. We can interpret the cardinality constraint as a single packing constraint. So on the left we have a covering problem, and on the right we have a packing problem. We showed previously that set cover is NP hard by reduction from 3-sat. We can use this fact to show that max coverage is NP hard as well. The proof is left as a healthy exercise. We showed how to approximate the set cover problem by a combination of linear programming and randomized rounding. For maximum coverage, we'll explore a different approach called the greedy algorithm. So suppose I have a bunch of points and a bunch of sets covering these points. Maybe my goal is to pick 6 of these sets that cover as many points as possible. Now suppose we choose these sets one at a time. Which set do we select first? One reasonable idea is to select this set in the middle, because it contains 8 points, which is as many as any other set I've drawn. Which set do I take second? If we're following the same strategy, then we should take the set that covers the most new points, which might be this one, which contains 4 points. Then we might take this set, which also covers 4 new points, that set, which also covers 4 new points, and then that set, which also covers 4 new points. This set also covers 4 new points. Now, there's no more 4 pointers left, so we might take that set, which covers 3 points. In this fashion, the greedy algorithm repeatedly selects a set covering the most new points relative to the sets we've already taken. Greedy is a simple and natural heuristic, but is it a good one? We now ask, how good, in terms of its approximation ratio, is the greedy algorithm for maximum coverage? When analyzing the greedy algorithm, we adopt the following notation. Recall that the sets are indexed from 1 to n. We identify a subset of indices S with the collection of sets indexed by those indices. We define a set function f over collections of indices as follows. For a collection of indices S, f of s returns the number of points covered by all of the sets with their index in the collection S. In terms of our new notation, the goal becomes to maximize the set function f of s over all subsets S of 1 to n subject to S containing at most k elements. As we analyze the greedy algorithm, we enumerate the elements taken by greedy in the first, second, third, and so forth iteration by E1, E2, E3, and so forth. For each I, we let S sub I be the collection of sets taken by greedy after the first I iterations. So for example, S sub 0 is the empty set, and S sub k is the set output by the greedy algorithm. We want to show that the total coverage at the end of the algorithm, f of s sub k, is at least some factor times the optimum value attainable by any k sets. This could, for example, be 1/2, or 1/4, or 1 over 2 to the 260, or 1 over log n, or 1 over square root n. We don't know, but we want this number to be as large as possible. The key lemma in the analysis is as follows. For each I from 1 to k, f of s sub I minus f of s of I minus 1 is greater than or equal to 1 over k times opt minus f of s sub I minus 1. The left-hand side can be interpreted as the amount our total coverage increases from the ith selected set. The right-hand side reflects the gap between the optimum solution and the solution we had before the ith iteration. Proof. Suppose this is the area covered by opt and this is the area covered by s sub I minus 1. Maybe there's some overlap. Let's look at the part that's covered by opt but not covered by s sub I minus 1. The number of points in this region is at least opt minus f of s sub I minus 1. Here we use the fact that opt itself consists of exactly k sets, so we can break the region into k parts depending on which point is covered by which set. Then, at least one of these sets must cover at least 1 over k fraction of this complementary region, which has at least opt minus f of s sub I minus 1 points. And whatever set is selected by greedy must bring us at least as much improvement as this set in the optimal solution. The overall analysis is as follows. We just showed that the improvement made by the greedy algorithm in each step is at least a 1 over k fraction of the difference in objective value between the current solution and the optimum. We can rearrange this inequality to get opt minus f of s sub I is less than equal to 1 minus 1 over k times opt minus f of s sub I minus 1. That is to say that the objective gap, the sort of room of improvement of our solution at the end of iteration I, is at most a 1 minus 1 over k fraction of the objective gap at the end of the previous iteration. The point being that the difference between the optimum value and the value of the greedy solution decays exponentially over the iterations. Initially, we have that the difference between the greedy solution and opt is of course equal to opt. After one iteration, the difference between the optimum value and the greedy solution is at most 1 minus 1 over k times opt. After two iterations, the difference between the optimum value and the greedy solution is less than equal to 1 minus 1 over k times the difference in the previous iteration, which comes out to 1 minus 1 over k squared times opt. After three iterations, the difference between the greedy solution and optimum value is at most 1 minus 1 over k times the difference after two iterations, which comes out to 1 minus 1 over k cubed times opt. Continuing this pattern for the fourth iteration, the fifth iteration, the sixth iteration, at the end, we get that opt minus the output of the greedy solution is less than equal to 1 minus 1 over k to the k times opt. We can simplify this further and say that it's all less than equal to e to the negative 1 opt by using our favorite inequality 1 plus x is less than equal to e to the x for all x. Rearranging this inequality, we get that the value of the output of greedy, f of s sub k, is greater than or equal to 1 minus e to the negative 1 times opt. This is about 0.6321 or so. In conclusion, we've established the following theorem, that the greedy algorithm will select k sets such that the total coverage of this sets, f of s sub k, is at least 1 minus 1 over e, the optimum maximum coverage of any k sets.